Hi everyone, this is the last video on set theory. I will not say it's a comprehensive set theories, slides which I have prepared. Fundamentally, I wanted to cover certain portion which can help you understanding the probability theory. That is the only portion which I wanted to cover. So let's talk about operations on sets. Previously, I have discussed certain other portions in operations on sets. You can see the other videos and you can find it out. I have already discussed some operations on sets. Uh, in fact, the correct word is operations on sets. That's the better way to write it. So let's talk about the first operation, very popular, called as union of sets. And this is the mathematical definition. If X belongs to B or X belongs to B, then X belongs to A union B. So this simply means what? Let me take certain examples. Let me take a set A which has some elements called A, 1 and 2, and there is a set B which has again certain element associated in it, 2, 4 and let's say 6. So if I want to find out A union B, then it is simply going to be A, 1, 2. I have listed all the members of A. Then I check whether there is any repetitive member in B. Yes, 2 is there, so it will not be repeated. Then you write 4 and 6. So if you see that set basics definition of set theory is to maintain the distinctness of the set. And when I say distinctness, I simply mean that you're supposed to be, I'm sorry, let me get back to the slide. Yes. So when I say distinctness, you're supposed to be pretty much sure about, that the number of elements are not repeated in the set. That's why this 2 hasn't been repeated. If I want to represent this entire thing by a Venn diagram, then how it is going to work out is this is set A, this is set B, that you can think of set A and set B. Now if you see, A has A, 1 and 2, while B has 2, 4 and 6. This is a universal arrangement and this represents A union B. Now another thing to notice here is the number of elements in A are 3, number of elements in B are also 3. We can see 1, 2, 3. So number of elements in A union B, if you see 1, 2, 3, 4, 5, they are 5. So number of elements in A union B can be given by number of elements in A plus number of elements in B minus number of elements in A and B. So if you see A and B, there is one element which is in common too, which will later be represented by intersection of sets, and that's how it is. If I want to go for a general representation through Venn diagram, this is a universal set. I want to represent A union B, and this is set A, this is set B, this is set A, this is set B. All this shaded portion will be known as A union B. So union of set is commutative. That means commutative. Sorry, you can whether you go for A union B or B union A, the result is going to be same. You can test it with the example above. Same way A union B union C. So if I put it through Venn diagram, it can be easily seen that there are 3 sets. This is A, right? This is B, and this might be C. So if you see you operate with A union B union C, this entire portion will be shaded. And if you operate through right hand side also, it will be shaded. I'm leaving you with an example. That means you can solve it by yourself. A has 1, 2, 3. The set B has, let's say, 2, 0 and 9, while set C has 2 elements A and B. Now you try to solve it, and first solve the left hand side. That means you can simply go calculate A union B, and the result needs to be operated with C. Same way, then you calculate the right hand side, where you can calculate B union C and operate the result with A. You're going to find LHS is equal to RHS, and the proof can be seeked. The other properties is law of identity. A union null set becomes A. So you just need to remember these things, and the proofs are very easy. And A union A is A. I'm recalling it that this is just the fundamental for the probability theory. That's why I'm skimming through it. Universal set union A becomes a universal set. Let's talk about the next operation, which is called intersection of the sets. If X is in A, X is in B, then X belongs to A intersection B. And very simply, if I want to represent it through a Venn diagram, a general representation, that is going to come something like this. This common shaded portion will be called as A intersection B. This is set A, this is set B, and this is a universal set. Another example, you can have A as 1, 6, 9, and B is, let's say, some set, and I'm writing it X such that X is a natural number less than 6, let's say. So it's very simple, you know. So if I want to write it in tabular form, so it is going to be 1, 2, 3, 4, and 5. Now if I see what is common between A and B, A intersection B, and is very important word here. Like in union, the or was a very important word here. So the common elements are actually 1, that's it, nothing more. 1 is in here, 1 is in here. So A intersection B is going to be 1. So that's the definition of A intersection B. Certain properties of intersection. Union of sets is this is all is intersection. I'm extremely sorry. This is intersection. This is also intersection. Intersection of sets is commutative. A intersection B is B intersection A. Intersection of sets is associative. The same property holds. The law of identity. That means any set A intersection null set is null set. A intersection A becomes A. Universal set intersection A becomes A. And this is an important law which is called the distributive law also, that intersection is distributive. So you know, you just don't have to go confused on it. You can simply think it this way, that you know, you can simply think it this way, that if let us suppose you have something like 4 multiplied with A plus B, so you simply write it 4 times A plus 4 times B. So same way, this is distributive. Union you can think as multiplication, you can think as multiplication intersection, and union you can think as addition. So it's no different at all. So it is actually means, if I'm more elaborative, I write it, so it becomes something like this. So that's how this distributive law simply works. And you can check with the proof by taking 3 sets, calculating the left hand side and right hand side. Then comes the complement of a set. The complement of a set means every element other than that particular set. So if I want to represent through a Venn diagram diagram that how complement of a set works, so it is represented by complement of a set. If this is set A, then this shaded portion becomes the complement. That means everything other than A will be the complement of sets. So if universal set is, let's say, I would say 1, 2, 3, 4, 5, 6, 7, 8, and this is the universal set, and set A is, let's say, 4, 5, and 7, then complement of A will become anything which is not here. 1, 2, 3, not in A, right? And then 4, 5, 7 are there, 6 and 8. That becomes complement of a set. This is the very means one of the major properties of complement of set, that complement of a set, complement of a set becomes the set itself. And you can try it from here, that if I take the complement of this, you will ultimately get A. So that's all about set theory, which was needed for the probability. So I'm going to stop it here, and then let's take some examples in the probability theory now.